Hello. So let's start for a session on Scala.js and WebAssembly, a tale of the dangers of the sea. When I submitted the talk, I felt like being very poetic. And then when you actually get to prepare the talk and the technical details, and then suddenly you realize maybe that was not a good idea. Um, but anyway, otherwise we'll of course stick to the content, but you might not see as many images of characters and Scala as you might have wanted. Also, fair warning, there won't be any demo in this talk. None of what I'm going to talk about works. So if you wanted to see something that works, you still have time to run to one of the other talks you wanted to see. So this is completely purely theoretical. If you were at Kelly's talk just before, she was talking about talk-driven development. When she submits a talk and then she learns or implements the thing she wants to talk about. That was kind of the idea that I did with this talk, except I didn't get to actually take the time to implement any of this. So this is all purely theoretical, but hopefully it will still be interesting. Okay, let me start by asking a small question. Basically, like, think about, for you, what is Scala.js? Like, is it a compiler? Is it a macro? Is it a language? Is it a JavaScript library? Is it a side project? Or is it an ecosystem? And I won't do a show of hands because it's too complicated. It takes too much time, and I haven't prepared nice online polls like the keynote. So let me just answer the questions for you. So it is a compiler. It is also an ecosystem, and for that I'm super glad that people in the community actually build libraries on top of it, because otherwise it wouldn't be useful. But most importantly, for the purpose of this talk, it is a language. So probably many of you thought that Scala was the language, and Scala.js is like the same language. So why is it really a language? Well, because it's actually relatively distinct from Scala JVM. I am very proud of always talking about how portable it is and how you can take any library and just change the build, and then suddenly it also compiles for the JavaScript platform. But the reality is there are also a few things that make it quite distinct from Scala JVM as a language. You might have heard of undefined behaviors. There was a talk yesterday that said if you access an array out of bounds, it will just do stuff instead of reliably throwing an array index out of bound exception or something like that. The toString call of primitive values is not quite the same. The type test as well. But those are details in the grand scheme of things, and especially for today, what is relevant is there is no Java interop, of course, but there is JavaScript interop. And that's actually a big part of what Scala.js as a language is. You can't just compile Scala to JavaScript and call it a day. That's the easy part. And when I say easy, I truly mean it. I did that in 2 weeks, I think. And then it took me 6 years to get to where we are now. So JavaScript Interop is really the soul of Scala.js. And it's more than just what people would call an FFI, so a foreign function interface. It's really bidirectional interoperability with objects, function values, state, properties, methods, all of that. You can call JavaScript things. JavaScript can call you in synchronous way, in asynchronous ways, using callbacks, using futures and promises, all of that stuff. So here you have an example code that mixes and match to the maximum I managed to do in 6 lines of code. JavaScript and Scala. So you have Scala classes like point, which is even a case class, and state, which inside contains some reference to a JavaScript array. And that JavaScript array contains itself points, which are again Scala constructs. And then you can call the add_event_listener method from JavaScript and give it a lambda. And that lambda is defined in the Scala code, but it ends up being a JavaScript function that holds in its captures the Scala states, and then it mutates that thing. And so basically, like, you can do this sort of stuff. We'll come back to this example in about 38 slides. In the meantime, let's go a little bit, talk a bit about what is WebAssembly, and that you might have even less of an idea. So is it a compiler? Is it a virtual machine? Is it a language? Is it a binary format? Is it specific to the web? I mean, you might want to expect that. Is it an open standard? So it's not a compiler at all. It's really a language, a binary format, and an open standard. And it's not specific to the web. And again, most importantly, for the purposes of this talk, it is a language. So it might not be a language that you might want to write by hand, at least not for more than 10 or 20 lines of code. So in practice, it's typically a language that is the result of compiling from another language. So this is a bit what WebAssembly can look like. So on the left, you have some C++ code, or C, or both. I never remember the difference. It's a factorial. It's not tail recursive. I never write tail recursive functions. I don't know what people have with them. And on the right, if you compile this with a C to WebAssembly compiler that is very smart, what you might get is the result on the right. This is not actually what you will get with typical compilers right now, but it's the easiest code I could find that kind of fits the bill. So you can see that it's basically a stack machine. So every instruction puts something on the stack or pops things on the stack, does computations. It looks like bytecode, but control flow is structured. So instructions are all linear, expressions are expressed on the stack, but control flow, like an if-else, is structured. So there are blocks of if and else. We'll look more into details later about what kind of things we can do. But you can see there that we have int64s, we have some primitive operations like sub, multiplication. We can call methods, including recursive calls and that kind of stuff. So basically, this is what you have in WebAssembly. You have a linear memory model. So the kind of what you would get in C, basically. So basically, the memory is one giant array of bytes. And you can have pointers into that array, which are basically indices into the array. And there is absolutely no GC. Okay, so this is what you get with WebAssembly right now. So WebAssembly can sort of talk to JavaScript, but in very limited ways, and in a way that I would, in this case, qualify as an Fourier function interface. This is way too much code, but what you can see is I have on the left some JavaScript functions that I somehow give access to JavaScript, to WebAssembly. In WebAssembly, I can import those functions. That's the fourth line on the slides. And then I can call them later down the line. This is an alternative text version of WebAssembly, which is more like Lisp. And the two versions are basically one-to-one correspondence. It's just a different way of expressing some intent. That was just for the show, and also because it was the output of the compiler I used. And I didn't want to translate to the other form, but I will stick to the other form for the rest of the talk. So here you can see that we have functions in JavaScript that take floats as parameters and return. Sorry, I probably mixed up. On the left, of course, you have some C code. So it takes floats, it returns floats or void, and that's about all you get. It's numbers, and that's it. So the FFI with JavaScript is really limited to passing 32-bit integers, 32-bit and 64-bit floats, and that's it. Like literally, this is the only thing you can like give between WebAssembly and JavaScript. So strings, nope. Objects, nope. Higher order functions, definitely not. Okay, let's get to the fun part, which is let's try and compile Scala.js to WASM. WASM is the short name of WebAssembly. This is how Scala.js works. Like now you understand all of Scala.js basically. You have Scala sources. You give them to the Scala compiler, to the Scala.js compiler. It spits out some SJS IR files, which stands for Scala.js Intermediate Representation. Very original. And then maybe you put that on Maven, or you pull other artifacts from Maven that contain those SJS IR files, and you give them to the Scala.js optimizer, which messages them, spits out optimized IR. And then there is a last step that takes that IR and outputs one big JavaScript file. So if we want to compile Scala.js to WebAssembly, we can reuse the sources, hopefully. We can reuse the Scala.js compiler. We can reuse the SJS IR files. Like we can reuse the Scala.js optimizer. To a large extent, some of the things it does are specific to optimizing for JavaScript, but we would just deactivate those parts. The one thing that we need to rewrite is the very last part, which takes the optimized IR and emits WebAssembly instead of JavaScript. So that means that I will show a lot of Scala.js IR in this talk, because that's our input format, really, for what we're trying to do. So to give you an idea what it looks like, here is a factorial function, again, the non-tail recursive one, but written in Scala above, or Scala.js to be precise. And if you compile it with the Scala.js compiler, you end up with this IR, which looks fairly similar. What you see is that all method names have a mangled name, so that overloading is compiled away. You have primitives like ints. Every operation is tagged with the type of operand it takes. Like the equality comparison is an equality of ints, not of something else. And it has structured control flow with if-else, etc. But it also has full-blown expressions, like the times operator and the method call, and inside the subtraction. And basically, the type system is very similar to that of Java at this point. So it's objects, classes and interfaces without type parameters. That's all erased away, and primitives. Okay, so let's take this IR and compile it to WebAssembly. So we can start at the top of the function, look at the if-else. It's structured, and we can compile it down to the structured control flow if-else of WebAssembly. So far, so good. Then you can see that the if in WebAssembly is annotated with I32, which means that the result of this if-else is an expression that returns an int 32. So it's like in Scala, if-else can be expressions and can return a value. We can compile the condition of the if, which comes before the structured if, because it's going to put on the stack a Boolean value that says yes or no. And so how we compile these things is we load the local variable 0, which is n, and we put it on the stack. Then we put the constant 0 on the stack, and then we compare the two things on top of the stack, and we put back the result. And then the if is going to pop the Boolean value of the stack, and if it's true, enter the then branch, and otherwise enter the else branch. This is how it works. So in the then branch, it's super easy. We have the constant 1. We can load it, put it on the stack, and that's it. So the thing that's on the stack at the end of the then branch is going to be the result of the if expression, right? In the else part, we can look at what's the topmost operation. It's the times. So at the very end, we're going to say multiply the two things that are on top of the stack. And on the left, we have the local variable n, which is, so we load the local 0, we put it on the stack. On the right, we first need to compute the argument to the method. So load n, put 1 on the stack, subtract, and we get something else on the stack, which is then going to be the argument to the recursive call to factorial. And then the result of that call will be on top of the stack, so we can multiply the two values. So this is really how it works. So far, it seems like we're good, right? The translation from the Scala.js IR to WebAssembly, this looks easy, super easy. We can even do a tail recursive factorial, because otherwise someone will kill me at some point. So this is the tail recursive factorial with an accumulator. And if you compile it with the Scala.js IR, with the Scala.js compiler, you get the IR that's at the bottom. It is fairly complicated. It has a few weird things, like those labeled blocks, this X, int, whatever thingy, then a while through, and then inside it has returns, but with a label that's like the name of a block. Anyway, we're going to look at it. I don't really want to go into too much detail of how this really works, but we have this weird construct, which is this labeled block and the returns. And the fun part is that WebAssembly has exactly the same weird construct that nobody invented before, and Scala.js invented it, and WebAssembly invented it, and they invented the same thing. So it's really nice, because that means that when we compile Scala.js to WebAssembly, we can map one to the other, because they mean the same thing. So here we can compile this thing. First, we're going to look at the local variable declarations. We're going to lift them out at the top, because WebAssembly only has local variables declared at the top of the functions. And then we start from the outermost part of the method, and we encounter this labeled block. So we emit in WebAssembly a block whose name is $x, and the returned value of the block will be a int 32. And then inside, we have this loop, which is a while true, so it loops indefinitely. So basically, in WebAssembly, what you would do is have a loop construct that has a name, and at the end of the loop, you branch back to the loop label. So it's going to loop indefinitely, except, of course, if from within the block at some point you exit it in a more brutal fashion. Inside, we encounter another labeled block, but this one, it returns void or unit or whatever. So we translate it to simply a labeled block in WebAssembly. And then we have the same kind of if expression here. So same thing as before. And the if is an expression. Again, we load the local, which is the accumulator. Then we have this thing to load n, put 1, subtract, store. Same thing with the multiplication, boring. And then we have this thing where we just move things around by loading locals and setting locals somewhere else. And finally, we have this return thing, which is really like jump at break from this label. So that's what we say, break from this label in WebAssembly. And it's the same thing. It's amazing. And we have the same with the return, but this return takes actually a parameter, and that will be the return value of the block. So at the end of the if else here, it's an expression if else, so it puts something on the stack, and this branch is going to pop that thing from the stack and return it as a result of the big block. So that's how it works. Anyway, this was just to show off that Scala.js and WebAssembly have the same kind of control flow. So yeah, for that. Now things get more complicated. Classes. As you know, Scala has classes. Here is a non-case class. It's just a final class point. And we have a method that just makes a point. And this is how it would be compiled in the Scala.js IR. So you can see a class that extends object. It has fields. It has accessors for these fields. And it has a constructor, which takes two ints, puts them into this, and calls a super constructor. It's really boring. And this is how you would somehow compile this to WebAssembly using the linear memory. So the important thing here, which apparently I forgot to highlight on the slide, is the fact that we have a call to $malloc. So we're actually like allocating memory from the linear memory, and then we're putting things inside, and we end up with a pointer really to the class. And we have to store things like a reference to what class this is, and then we store the values, etc. And we call the constructor, all of that kind of stuff. And here is the body of the constructor, which also calls the super constructor and then stores things inside the fields. It's relatively straightforward. If you imagine that an object lives in a linear heap and you have memory that you have to fill in, right? And then we have a lot of things that we need to encode from Java or Scala is the same thing basically at this point. Virtual dispatch, interfaces, garbage collection. You can implement all of that. It's possible. It's very tedious, but it's doable. And then comes the interoperability problem, and this is the attack of one of the monsters of the sea. But yeah, so here is a simplified scenario in Scala.js where I would use the JavaScript timers, especially the global function set timeout. I give it a function, I give it a delay, which is basically a number. And this is how it would be compiled to the Scala.js IR. So you have, we have access to the global set timeout function, and then we have a call, and then we have an arrow lambda. So basically a JavaScript anonymous function. That lambda calls another method, and that method also gets the global console object, calls the log method with a parameter hello as an argument. And here things are problematic because just look at the last line, which tries to write hello on the console. This thing wants to read access to a global JavaScript value, which is an object. It's console. Problem: there is no such thing as an object in WebAssembly, so you can't even take that in your hands. You have no handle to this thing, which is a JavaScript object. You cannot talk about it in WebAssembly. You have strings. You cannot talk about strings in WebAssembly, but you can put this array of cars in the memory, but those are not JavaScript strings. They're C strings. You cannot hold in your hands a JavaScript string, so you're stuck there as well. And then you have this method call to a JavaScript function, which is even more complicated. Like we cannot even talk about the things that make up this function call, let alone the function call itself. And above, like imagine, like you have a higher order function. Like what do you do with these things? So WebAssembly just doesn't have the ability to talk about these things. You can't get access to any of these things. So if you write that in Scala.js, like it's done, right? So are we completely stuck? Like, is this the end of the talk? And well, there are a few things we can try. One is let's drop interoperability, maybe. I don't know. That's the other monster. If we do that, well, we basically lose all attempt of any kind of portability of our code, right? The Scala.js code that has been written for several years just won't work. And what you end up with actually is a different language. You basically dropped interoperability from Scala.js, which was the soul, for which Interop was the soul of Scala.js. So what you get instead is another language. You might have heard about it. It's called, any idea? Scala Native. And this is the third language that you might want to experiment with. There is Scala JVM, there is Scala.js, and then there is Scala Native. It's a third language. That language can be compiled to WebAssembly, but that language doesn't talk to JavaScript. So it's a different language, different trade-offs. And that's not my project, so I don't care. Okay, so what we could do instead? Well, basically in WASM version 1, the WASM that is available today in your browsers, we are actually completely stuck. There is nothing we can do about it. So Scala.js is dead. But there is hope in proposals for future versions of WebAssembly. So now we start looking into the future of what might be possible. And there is one proposal which is about reference types. You can go and click on that link if you want, but I'm going to present a little bit what it does. So basically, the reference types proposal is an extension to add, well, basically one type to WebAssembly, which so far had integers, floats, and doubles. And now it has 4 types. It has also any ref. And an any ref is a reference to something from the host environment. It could be the JavaScript heap, for example. So it could be a reference to a JavaScript object, or it could be a reference to a JavaScript string, or it could be a reference to a JavaScript number, because that's also a JavaScript thing from the host environment. And you can have any ref on the stack for local variables, for parameters to functions, as a result of functions. And you have also a separate heap that is distinct from the linear memory in which you can store any refs. So you still have the giant array of bytes, which is the linear memory, on which you can basically put bytes. And then there is another array of any refs. But you cannot put any refs inside the linear memory. That's not possible. And you cannot cast an any ref to an int pointer either, because otherwise the JavaScript GC would have issues. Okay, so what can we do with that? Well, let's look again at our hello method, which was impossible to get before. Now it's only very awkward. So what we can do is decompose the things. So the first thing we need to do is read the global variable console. And for that, on the WebAssembly side, on the right, well, you can't really, there is nothing in WebAssembly, even with reference types, that lets you access a global variable from JavaScript. The only thing you can do is import some functions from JavaScript. So you can write a function in JavaScript on the left that is called getConsole that returns the console. And you can import that function from WebAssembly. And then you can call that function. And it doesn't take any parameter, and it will put on the stack the result of the function, which is the console object, which is an anyRef. OK, so far so good. Then I have to put the string log on the stack. But WebAssembly doesn't know how to create a JavaScript string. But it's not a problem. We can write a JavaScript function that returns the constant log, which is a string. And we can import that function, and we can call that function, and we receive the string as an anyRef. And we can do the same with the other constants in our program, like the string hello. And finally, when we've put those 3 things on the stack, the console object, the log string, and the hello string, we want to call the method. But WebAssembly doesn't know how to call a JavaScript method. But it's not a problem. You can write a JavaScript function that is going to call a method. And you call that method, call method 1. It takes an object, a method, and an argument, and it's going to call the method. And then you can import that function from WebAssembly, and you can call it. So you've called things from JavaScript outside to put things on your stack, and then you called another JavaScript function to actually use those things from your stack. So that's good, right? We managed to print something, which is a step up from before. Let's look at the set timeout thing with the lambda, right? Can we do something about that? Yeah, it turns out we can. It's just very awkward, but we can create a function in. So actually, this one is relatively easy because it doesn't have any captures. So we can actually write a function on your right with which is a WebAssembly function that is the lambda, and it doesn't take any argument, and it returns an any ref, and it calls the other actual methods. And you can actually use this ref.func operation in WebAssembly to get a JavaScript version of that function. So that's possible, but only because it doesn't have captures. But that's already quite good. So you can put that on the stack. And then you can put the constant 1000 as a double on the stack. But then you cannot actually give that to JavaScript, at least not in a relatively generic way, because what you want is really any refs. So what you need is a function that takes a double and returns an any ref for that double. And WebAssembly doesn't have an operation for that. But no problem, you can write a function in JavaScript on the left, which is called box double, that takes a double and returns the same thing. So that was useless, right? Except that if you look on the right, we give a type to that function from WebAssembly side, and we say it takes as a parameter an F64, so a double, and it returns an any ref. And because of how WebAssembly and JavaScript talk to each other, the double that was on the stack will be given as an F64 to JavaScript, which returns it into a primitive number. And when it returns to WebAssembly, which expects an any ref, that number will be interpreted as an any ref version of that number. So yeah, for that. Now that we have those things on the stack, we can use a similar mechanism to actually call the function, etc., etc. Okay, so we can do that. But here's a real problem. References across heaps. Because remember I told you that any refs, you can put them on the stack and on a separate heap. But you cannot put them inside the linear memory. So I told you we were going to come back to this example. And here is a schematic version of the references across the two heaps that we need here. We need in the JavaScript heap, at the end of the day, we end up with a DOM event listeners thing from the browser, which reference a lambda, which is a JavaScript function. That JavaScript function, in its captures, has access to the state thing, which is an instance from the Scala heap. And that thing contains a value points, which is a JS array, so it comes from the JavaScript heap. And that thing again contains points, which are things from the Scala heap. So now you have this thing. And, well, from pointers from the JavaScript heap to Scala heap, well, the only thing we can remember that on the Scala heap, objects are just pointers in the linear memory, so basically they're numbers. So yeah, you can hold a number in JavaScript, that's okay. But the problem is then that the Scala GC cannot know which objects are reachable or not, so it can never garbage collect anything. And then the other arrows from Scala to JavaScript, since we cannot put any refs in the linear memory, what we're going to do is put IDs, integer IDs, that are basically keys in a map in JavaScript that will actually map to the real objects from the JavaScript side. But then the JavaScript GC can never know when these things are unreachable. And you can make this work to some extent, But if you do have cycles at some point, then it's dead. Like your cycles are never going to be collected. And I don't even want to talk about the performance aspect of these things. Right? So what you really need at some point is full cooperation between the two GCs, the GC from the WebAssembly Scala side and the GC from the JavaScript side, because you need to support cycles between the two heaps. Like Scala is full of cycles, JavaScript is full of cycles, Scala.js is full of cycles between the two. So if we don't have support for cycles, it's a no-go. So with any refs alone, we can get far. We can actually get something that is correct, that will implement the entire Scala.js specification correctly. But there is just one little caveat. It won't garbage collect. I don't know, might be good enough for you. Okay, so then what? Well, there is another proposal for WebAssembly, for a GC. So I'm very happy about this one. It's at a very vague stage, though. But there is a document that says more or less what they want to do. And basically what they want to do is two things. They want new types, in addition to the integers, the floats, and the anyrefs. They want tuples and arrays. And then they want references to those things. So you can have, it's not a pointer, it's a reference. You can have a reference to a tuple or a reference to an array. And those references will supposedly be garbage collected. Like you can actually create a garbage collected heap in WebAssembly that will be taken care of by the WebAssembly GC. And that one is designed to cooperate with the JavaScript heap and the JavaScript GC. So that's good. So let's look at what we could do here. So for the class point, which has two ints, we would define two types. First, the type point struct, which defines the internal representation, which is actually 3 ints, not just 2. The first one is just an identifier for the class point, because we need to remember that for isInstance of and that kind of stuff. And the 2 other ints are the actual x and y. And then we define another type, which is point, which we define as a reference to a point struct. And the state is similar. Here it has a struct with an int, which is again the class state, and then an anyref, because that's a JavaScript array. So here in the structs, we can actually have anyrefs in this thing, right? So we can have gseed objects in WebAssembly that actually refer directly to gseed stuff from the JavaScript world and vice versa. So yay for that. So if we had that, or probably we will have it at some point, this is what we can do. So first we create an empty array, but of course WebAssembly doesn't know how to create an empty JavaScript array. But that's okay. You can write a function in JavaScript that creates an empty array and returns it to WebAssembly as an anyref, right? And you can put it on the stack. Okay. Then there is allocating an instance of state. First, you would put on the stack the identifier that for the class state. And then you put a null on the stack, which will be the initial value of the points field. And then you call this operator from WebAssembly with the GC proposal, which is new. And then you give the type of a struct, and that will allocate a struct with the initial values taken from the stack and return you a reference to that struct, not a pointer, a reference. And then you can call the constructor, which will take the reference, fill in the field, etc. So that's good. And later, when you want to create the lambda that has captures, and it has a capture of type state, which is a JavaScript, a Scala object, and a reference div, which is anything because it's a JavaScript thing, you can actually do that. You just have to, well, WebAssembly doesn't really know how to create captures for functions, but that's okay. You can write a JavaScript function that will capture things for you, and you can call it. And this is how you do it. So basically, if we have this GC proposal, at some point we will be able to encode all of Scala.js to WebAssembly with reference types and the GC proposal in a way that's correct and that actually garbage collects, which would be a good thing. So when do we get this? Well, first we need a reference types proposal, which is at a stage called implementation stage currently for WebAssembly. So that means the engines are encouraged to implement whatever the spec says at the moment so that we can get feedback on the proposal. And so far as I know, the Firefox engine implements the current state of reference types. Then we need the GC proposal, and that one is at a very early stage. There isn't even a spec at this point. It's ideas for a type system, more or less specified, but not really. So that will take some time. And then when that's done, then we can actually implement the support in Scala.js, or at least we hope to actually do that in parallel with the development of the GC proposal so that we can feed back into the proposal if something is wrong for us. So it will still take a while. I'm sorry about that. So that's all I had. I'm happy to take one or two questions. I think we have a few minutes. Thanks. The microphone is coming.
Thanks for the talk, Sébastien. I'm wondering, because there's another path that can be taken, but I wonder why it cannot be taken here. For example, maybe you saw what, I think it's Asterius, the name of the project, which is basically a GHC backend that goes to WASM. And I think what they do is that they serialize the values between... is it because Scala is not referentially transparent that you cannot do it?
There is, yeah, so certainly if your language is entirely referentially transparent, you can do that. You can serialize,
and you have another GC that you have to implement in the WASM, but then you can serialize back and forth.
But it's a bit of a lie, though, because what if you need to serialize a value of type IO?
Well, you never do that.
Well,
in Haskell, you never do that.
Yeah, but the thing is, like, this is the kind of expressivity in terms of communicating with JavaScript that Scala.js has, and that a language that doesn't have this binary synchronous interoperability with JavaScript, like everything you can do in JavaScript, you can do it in Scala.js. If you cannot serialize an I/O, basically a state in between two calls to JavaScript.
What would be a concrete use case of that, where you will need to send that I/O?
The small snippet I showed earlier, which interleaves calls to mutable JavaScript things and my own code, and then calls again something from the JavaScript world.
But then when you are in WASM, how can you call the external world? How can you launch a missile, right?
Yeah, you can do that because you can import JavaScript functions, which we did with the import statement, and
yes,
we called it.
Yes, but I mean, if you take that path, you do all the communication between that interface, right?
It gets unwieldy, and at some point you realize you can't get everything right. But if you want, we can talk further offline. Any other question? There at the back.
Hi, Sebastian. So I guess my question would be this: what you presented would work, but what would be the advantage gained over the current encoding? Like, is it worth the big change in encoding and possibly all of the overheads for all the stubs that you are forced to implement in order to just move to a different runtime versus what we already have now as a thinner translation to JavaScript? Like, what do you think of the relative pros and cons of the two approaches, given that they both can work?
Well, nobody really knows. If you ask random people on the internet, they will say compile to WebAssembly is going to be fast. No, that's not how it works. If you compile C to WebAssembly, it's going to be fast relative to compiling C to JavaScript, because compared to C, JavaScript has too many features, and recovering them to the level of C is problematic. So this is why WebAssembly was invented in the first place, which is going from C to WebAssembly, you don't have the impedance mismatch. You're not losing things, but you're also not gaining anything. If you compile a garbage collected language to WebAssembly, with the GC proposal, hopefully you expect to not lose things, and that's how you gain performance. You only gain performance in WebAssembly because going from your source language, you're not losing things. So what things would we not lose? Well, we wouldn't lose, for example, our types, or at least our monomorphic types, the same kind of types we have on the JVM. So as long as you're staying in your compute intensive or some portion of your program that only manipulates Scala types, you remain in the realm of WebAssembly where everything is statically typed. And in theory, you can get something similar performance to the JVM. Except that, of course, the JVM is going to do polymorphic inlining and that kind of things, which in WebAssembly right now is still a no-go. Like you cannot do profile-based optimizations at runtime. Like this is not happening yet. So I think what we can gain, if really all of this happens, is for the large portions of Scala.js programs that actually stay within the Scala subset, those will basically perform better. But if you have a portion of your Scala.js programs that constantly talks to JavaScript back and forth, that might actually lose performance because it would constantly cross the boundary between WebAssembly and JavaScript. And depending on how that's implemented at the engine level, we could lose performance, or at least we won't gain anything. That's definitely the case. And then for things like virtual dispatch and inlining of those things, it's unclear. The future is still very much uncertain at this point.
Yeah, thank you for the talk. Maybe a crazy question. So, do you think it's possible to compile the JVM itself in WebAssembly?
Yes, it's been done.
So then the Scala.js code can become bytecode, and the JVM can interpret.
Nope. The Scala JVM source code can become bytecode and can be interpreted by the JVM. But again, it's the same problem as with Scala native. It's a different language. And if you write Scala JVM code, you can call Java libraries, but you cannot call JavaScript libraries. You cannot manipulate the DOM. You cannot manipulate your web page. You cannot use the zillions NPM packages out there. So again, it's important to go back to the semantics of your language and remember that Scala JVM, Scala.js, and Scala native are three different languages with different semantics and different capabilities. And yes, you can compile a JVM to WebAssembly and you can run Scala JVM code on that VM, but you cannot run Scala.js code on that VM.
The last question.
Thanks. Thanks for the talk. It sounds very exciting, and I look forward to things happening in WebAssembly so that they can also happen in Scala.js. I was wondering if on the Scala language side, we got effects. Would that improve the performance or pose opportunities for certain kinds of optimization? Since we mentioned what GHC is able to do, and also obviously garbage collection here is important. So if you could establish that certain parts of code don't do certain things, how much do you think this could help? So to not always optimize for worst case, so to say.
Do you have funding for a PhD student?
Maybe we will.
I think it's a it's really a research topic. Like we don't know how to do these things. Like given the current hardware and the current optimizers, and it's still unclear what an effect system is actually able to provide in terms of optimizations in general. So let alone in the constrained environment of WebAssembly. I think this is it's worth thinking about it, but yeah, as my initial answer suggested, I think it's probably worth an entire PhD. Yeah. Thanks. Okay, I'll be happy to take further questions here or after the talk. Thanks.